Okay. All right. I'm too quiet this time. All right, everybody. Today we are going to continue talking about hidden Markov models, and in particular, we're going to extend what you saw last time about inference in hidden Markov models to a sampling-based technique called particle filtering, and we'll also see some applications of these methods. We'll see even more applications towards the end. The overall structure of this course, remember, the beginning was about choosing actions. The middle has been about reasoning about uncertainty. The last chunk of the course will be about machine learning. And then at the very end, there will be a section on applications where we'll see a bunch of different techniques that we've seen throughout the semester show up. Hidden Markov models will feature prominently because this basic idea of reasoning about underlying phenomena over time on the basis of noisy observations is a really important one. And that overall framing backs a lot of modern problems in AI, though the specific techniques that we use do vary. So today what we're going to do is we're going to talk about, quickly recap hidden Markov models from last time. We're going to talk about particle filtering as an approach to doing inference. Particle filtering partially is something we do. Uh-oh. Yes? All right. Can people hear me in the back? Okay. All right. I think for once I'm just quieter than expected. All right. How's that? I also just got louder. So, all right. So if everyone can hear, let's find that train of thought. Was particle filtering we partially do in the real world because it's efficient, especially when your event spaces are very large or continuous or infinite. It can be a very powerful technique, but it's also a really useful way of understanding what's happening in the exact case. Because sometimes it's easier to think about tracking a particular particle or a particular sample instead of tracking sort of the exact space in aggregate. We're going to see a bunch of demos to illustrate what goes on in these exact and approximate techniques, and if there's time, we'll start talking about most likely explanation queries, which are used for a lot of things like speech recognition, where you're interested not only in tracking something over time, but in reconstructing the trajectory it took over time. We'll see some applications today. Robot localization and mapping are going to feature prominently, as well as some ghost busting, and later on in the course, we will see a little bit of information about speech recognition. So, to recap, last time you saw a couple instances of reasoning about how a random variable evolves over time. The simplest instantiation of a random variable evolving over time is a Markov chain, like what's shown here. In a Markov model, you have some variable x that replicates at every time step, and you're interested in watching how its value evolves probabilistically over time. In order to do this, we need to supply you with a couple pieces of information so that you can ask questions like, what's the probability of this variable on day 3? And so we need to give you an initial probability distribution, so some initial marginal probability over x at the first time step. And we also need to give you a transition probability matrix. These are sometimes referred to as the dynamics of the model, and this represents the probability distribution over this variable x given its value at the time before. So what this tells you is this tells you probabilistically how this variable evolves. If this variable is a variable that is unchanging, this will be a big diagonal matrix that just says whatever you were before with probability 1, you'll be the same thing at the next time step. Usually something more interesting is happening. So the example you saw last time is over here on the right, and this is a very, very simple Markov model. Here, the random variable x takes on the value rain or sun and represents a simplification of weather. And this thing on the right, if you look at it really quickly, you say that's the strangest Bayes net I've ever seen because the arrows form cycles, and some of them are even pointing at themselves. It's not a Bayes net. So on the left, that's a Bayes net. So even though we talk about hidden Markov models and Markov models as special cases because we feed them to you in time slices and then they unroll over time, this here is a Bayes net. Over here, this is not. This is in fact more like a finite automaton. The circles on the right represent the states of this Markov model, and in particular they represent elements in the domain of the random variable x. So here x can take on the values rain or sun, and the probabilities are represented here by the arrows, which show what state transitions are possible, meaning probability non-zero, and the numbers or weights on those arcs, which represent the probability. So it says, for example, if it's rainy today, 70% chance of rain tomorrow, and 30% chance that it will transition to sun. This kind of a network structure is really useful for specifying the structure within the different states and how they can interact. This is useful for things like speech recognition, where not all states can connect up to other states. When you see these, don't confuse them with Bayes nets or try to run variable elimination on them. They are representations of probability tables. All right, so you have a Markov model. And if I give you a Markov model, shown as a Bayes net on the left, and I give you the specific probabilities that live inside it, shown on the right, what can you do? Well, there's not a lot you can do. You can do things like say, if yesterday it was sunny, what's the probability of rain? Or what's the probability of rain 5 days after it was sunny? These are computations you can do on a simple Markov model like this without any evidence or observations, like we'll see in a hidden Markov model. There are other uses for Markov models that you talked about last time, I think, like, for example, looking at the stationary distribution. That backs some algorithms like PageRank, where that quantity is important. In a hidden Markov model, which is much, much, much more useful, you have not only the random variable x, which tends to be the variable that you're trying to track or reason about, you also have another class of variables that you see at every time step, which are your noisy observations of something that's connected to x. They may be an observation of x itself, they may be a sensor reading, but what you have now is, in addition to at each time step knowing how the variable x evolves, you also have evidence, and you're armed with a table that shows you for any value of the underlying state x, which you don't observe, what the probability distribution over evidence values is, which in general you do observe. There are other questions you could ask of this Bayes net shown here as a hidden Markov model, but the one you usually ask is, given evidence at every time step, either what is the current distribution, the current posterior distribution over the variable x given all my evidence to date, or I ask the question, what sequence of x values was most likely given the evidence I've seen. In this case, P of E given x says something like, when there's rain, you usually see the umbrella, and when there's sun, you usually don't see the umbrella. If you'll remember, this was a case of something like maybe a security cam robot that doesn't get to see the weather, but sometimes sees you walk in and out with or without your umbrella and has to reconstruct something about its belief over the variable that represents weather. All right, so these are Markov models, which we won't say much more about, and hidden Markov models, which we're going to say a lot about. Let's see an example. All right, so here is our Ghostbuster grid. What is this showing? This is going to show at all times our belief distribution over the random variable ghost location. What's a belief distribution? It's the conditional probability of that variable given all the evidence to date. And right now there is no evidence to date. So how can I change this? Well, in a hidden Markov model, you'll notice that there's a very regimented structure, which you'll have to modify to make more flexible in your projects. In the hidden Markov model, every time step, you get some sort of evidence, and then time elapses. And then more evidence comes in, and then time elapses. So if I were going to simulate that here, I could say, I'm going to get some evidence. And what that does is it reshapes my posterior distribution, knowing that the ghost is medium far from that point, probably. Now, if I let time pass, this ring that represents my belief distribution, what's going to happen? It's going to get moved around through the dynamics of the model. And you can't see in this visualization what the probability of ghost position is given the previous ghost position, but let's imagine I know that the ghosts tend to sort of wander around clockwise in a circle. So you can see that diamond of higher probability has been sort of pushed along that whirlpool there. So in a hidden Markov model, then I will get more evidence. Notice that when I get this evidence, it tends to sharpen my belief distribution. Okay, it's easier to localize the ghost after I get information about its position. That makes sense. But then when time elapses, not only does this probability sort of swirl around a little bit, it also flattens. And this makes sense too, because I'm not totally sure where the ghost is, and as time passes, I become even less sure, because its movement isn't deterministic. So in a hidden Markov model, I would get another piece of evidence, time would elapse, get evidence, time elapses, and you can see that I'm slowly accumulating, in this case, some certainty about the position, but I'm never totally sure. Okay, now I'm pretty sure. And if I stopped collecting evidence and I treated this like a Markov model instead of a hidden Markov model, what's going to happen? Right now I'm pretty sure where the ghost is. Okay, I'm super sure where the ghost is. And if I let time pass, my belief distribution gets flatter and flatter because the possibilities that could unfold kind of drift further away from that most likely position. All right, so that gives you a sense a little bit of what happens when time passes and what happens when you get evidence. And those are the two pieces of those are the two building blocks that we're going to use, both in exact inference and in sample-based inference with particle filtering, to construct and track our belief distributions over the random variable x. So there's basically two pieces we can break that into, and we want to wrap our heads around the math because it's basically these two little building blocks that get used over and over. So the first case is this passage of time. I don't exactly know where the ghost is. I don't exactly in general know what value x1 takes, but I have some distribution. And I'd like to say something about that random variable at the next time step. I'd like to predict forward one layer. Predicting forward involves taking my belief distribution and advancing it through the dynamics of the model. We'll dive into that. That's going to show up over and over. The second base case is I have some distribution over the random variable x. I think the ghost is about here. Then evidence comes in. That evidence will also reshape my belief distribution. And from these two building blocks, you can do any kind of updates of getting a bunch of evidence or letting time pass for a while without getting evidence. You can do it in the exact case and you can do it in the sampling-based case. So let's dive into these two cases. All right. First one. The first one is I'd like to know the distribution over x based on what, right? So let's say I want to know the distribution over x at time 2. Well, what do I know? In general here, I'm going to know the distribution at the previous time step. So what do I know? I happen to already know p of x1. Why? Well, it could actually be that I've observed x1. That would be extra easy. But maybe I know it because it's given to me on the first time step as a known in the problem. Or maybe I've already done inference up to this point and I know it conditionally on some evidence which isn't shown here. We'll expand this base case to condition on evidence as well. But let's say I'd like to know p of x2, but what I'm given is p of x1. How am I going to do that? Well, the way I'm going to do that is I'm going to break that into two steps. In the first one, I say, well, for any given value of x2, p of x2, I can rewrite that as p of x1, x2. Remember, x1 is for the first time step, x2 is for the second time step, summed out over x1. So this rewrite here that says p of x2 equals p of x1 comma x2 summed over x1, whenever I write something like this, what you should be thinking is, why was this allowed? Otherwise you start to get to feel like you can throw in variables and commas and conditioning bars everywhere and sum things out and whatever you write is going to be true. That's not true. Almost anything you can write about probabilities will be false. Why is this one true? You want to think, is that because of something I know about in HMM, or is that just laws of probability? What's this one? This is just laws of probability. You can always take any p of a and say, hey, that's the same as p of a comma b if I sum out all the values of b in whatever random variable b belongs to. That's always true. Okay, that's introducing a variable and marginalizing out at the same time. All right, well, how does that help you? Well, that helps you because p of x1 comma x2, that is the probability of x1 happening and then x2 happening, is just the probability of x1 happening in the first place, which remember we know something about, and the probability of x2 given x1, which is an element of the transition probability that was given to us when we were handed this hidden Markov model. Or in this case, just Markov model. Okay, so when can I do this? I look at this and I say, is this because of a property of an HMM or is this because of a law of probability? In this case, this is just a law of probability. When we do this in general with evidence, we're going to need to know conditional independence properties from the HMM. But right here, I've just written here the chain rule in its simplest form, the product rule. All right, so what does this mean? This means that if I know probability of x1, and I'd like the probability distribution over x2, for each value of x2, I say, well, you had to come from somewhere. You had to come from some x1. I know how likely each x1 is, so I write the probability that you started at that particular x1 and then went to our the current value of x2 we're considering from there. So these are all the ways you can end up in x2. You could start at this x1, that x1, that x1, and then transition here. And then you repeat this computation for every x2. Okay? So the transition probabilities say, hey, if your ghost was here at x1, here's all the places it could be at x2. But this computation says, hey, what's the likelihood that the ghost will be here at x2? And then you consider, well, you could have started here, 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 and you compute all the ways of getting to that x2. And for each one, you weight it by the probability of being there at x1 times the transition probability. This idea that you think about all the ways to get to a certain state by considering the ways you could have gotten there, that's going to be the backing of the dynamic programs like the forward algorithm, which you saw quickly last lecture. Okay, any questions about that? All right, so that we wrote basically without using the fact that this was a Markov model or a hidden Markov model. The hidden part won't show up until we have evidence. So we're going to have to use somewhere the conditional independence of a Markov model, which says that the past is conditionally independent of the future given the present. All right, so let's say we know something other than P of x1. Let's say we have a belief about xt. Say, what's B? Okay, this is just shorthand. It's actually kind of sloppy shorthand that people use to indicate that this is a belief about variable xt. But with a probability, when I write P, I have to be very, very careful what I condition about, because P of xt, that's a marginal probability of xt. P of xt given E1 through T, that's a conditional probability conditioned on the evidence. They are not the same. With belief distributions, when I write B, sometimes I'm sloppy. If you're ever confused on homework or exam and it's not clear in the context, please ask. But here on this slide, imagine we have a belief over xt, which is equal to some already computed conditional probability over xt given the evidence up to time t. So I've been tracking the ghost. Here is the probability. All right. Then I want to know, what should my belief look like after one more time step? Well, what is that? As a probability, I now want to compute the distribution not over xt, which I already know. So this thing here in the box, that's known. That's sitting there in a vector in memory, ready to be accessed. I'd now like to compute, given the same evidence, E1 through T, I'd like to compute the probability distribution over x at time t plus 1. What does this look like visually? This looks like I have a hidden Markov model here. So now evidence is coming into it. I have a hidden Markov model here. It was x1. This went all the way up to xt. There was evidence at each time step. So there's all this evidence. Here's evidence 1 all the way up to evidence t. And all the evidence is shaded, so I know all those nodes down there. And I currently have the probability over that node. What is going on with the ghost right now at time t? And what I'd like to do is I'd like to project that forward one time step to xt plus 1 without observing any new evidence. The evidence will come. So time's going to pass. I'd like to compute this new conditional probability. How am I going to do it? I'm going to write down a bunch of conditional probability statements that are licensed either by the laws of probability or by something I know about a hidden Markov model's conditional independence, until I can reduce the thing I'm looking for in blue, which I don't know, to some computation involving known things. So the first thing I can do is I can introduce this variable xt. I'm curious about the value at t plus 1. I can throw in the value at xt and sum it out at the same time. This is just introducing a variable. Okay, so xt popped in here, and it got summed out. The next thing I can do is I can decompose this conditional probability. I can say the probability given my evidence 1 through t of generating xt and then xt plus 1 is just the probability of generating xt, and then once I've done that, generating xt plus 1. This isn't exactly how you usually see the chain rule, but this is also just true from the laws of probability. If you write out all these conditional probabilities, everything will cancel out. So far, what have I accomplished? I've done some manipulation, and this value that I already know, which is the distribution at time t, given the evidence up to t, has appeared, and now I can plug those in. I don't need to simplify that anymore. But this part over here, the probability distribution of xt plus 1 given xt and e of 1 to t, this still needs to be simplified because this is not provided by my hidden Markov model. However, what my hidden Markov tells me is that xt is conditionally independent of all evidence before it given xt plus 1. And that lets me simplify that expression down to a transition probability. So this says something pretty intuitive. It says, if you want to know how likely it is, given some fixed evidence, of being at some xt plus 1, you just think, what are all the different ways I could have gotten there? Well, I had to be somewhere at the previous time step xt. So I'm trying to figure out how likely is it to get to xt plus 1. So I think of all the ways I could have gotten there. I could have been at all these different values for xt. Each one has this probability given the evidence. And then the probability of doing that transition is the transition probability. So I had to start at a certain place. I had to transition to my current xt plus 1, and then I'm done. I add those up. All right. So to write that compactly, you'll sometimes see something like this. This says if I have a belief distribution, yes, it's conditioned on the evidence. Yes, I didn't write that out. For time t, and I'd like to know the belief at time t plus 1 without any new evidence, I just take that old belief distribution and I multiply it by the transition probabilities and add things up appropriately. Okay, this is sometimes called pushing b of xt through the dynamics. Yep. Why do we have this b prime? Oh, yeah. xt plus 1. Yeah, sloppy PowerPoint, sorry. xt plus 1 would be more correct. Thank you. All right. So the basic idea here is you have some belief distribution, and it gets pushed through the transition. If you actually knew where the ghost was, if you knew the value of x at time t, it would be just the transition probability from there. But since you don't know, you sort of get a superposition of those transition probabilities weighted by the likelihood. All right. So what happens as time passes in the absence of any observation? As time passes, uncertainty sort of accumulates. So even if you knew exactly where that ghost was, or the exact value of variable xt, if time starts to pass, well, after one time step, even if you know the value of xt, at the next time step, all you know is where it would go. And so the sharper your transition probabilities are, the more deterministic they are, the more you're going to know after a time step. But if there's a lot of things that could happen, even after one time step, you're starting to be unsure. And if you push things 5, 10, 100 steps into the future, you stop being as certain as you were because of the simulation. This is a general tendency. Is it possible to be uncertain and then let time pass and have your certainty increase? It's definitely possible. If I had transition probabilities that said that wherever you are, you go towards the lower right corner, and I said the ghost is somewhere, I don't know where, uniform probability, right? It would say 0.2 everywhere or whatever. And then if I advance time, that probability would sort of slowly push itself into the corner, and after 1,000 time steps, I would be sure that by now, surely the ghost had made it to the corner. So there are transition probabilities for which the stationary distribution, which is basically what this is computing, is actually very peaked. Even if you don't have a sharp transition, even if you don't have a sharp initial probability distribution. Normally it goes the other way. Normally you have some knowledge and it decays over time. And so the picture here is more like you have your robot and it starts off with some clear sensor reading, and if some time passes without any more sensor readings, it gets a little confused. And then if enough time happens, it has no idea. Okay? We saw that in Ghostbusters as well. Okay, here's the other base case, and then we'll translate these into this new particle filtering algorithm. The other base case is I have some probability. So here we imagine the known is p of x1. I have some distribution over a random variable, like the ghost position. Maybe it's conditioned on a bunch of evidence. We'll get the evidence here in a couple slides. But I currently have a belief distribution, and evidence comes in. When time passes, I take my belief distribution and I reshape it through the dynamics, which sort of in a fuzzy way pushes it forward through that transition probability. Here, time isn't passing, but I'm going to get some evidence. So I'm going to go from p of x, which is a known quantity, and try to compute P of x given some evidence. Well, in a way this is easier, and in a way it's more complicated. It's easier in that we're still going to work with x1. All we have to do is figure out how the evidence reshapes our beliefs. And this should be fairly intuitive, because if I'm not sure where in this room my robot is, and it takes I don't know, how close am I to the wall reading, and it gets really close, suddenly I don't think it's in the middle of the room anymore. So evidence should reshape my probabilities, and it should do it in sort of an intuitive way. When I get evidence, the underlying states X that are more compatible with that evidence should come to dominate. How exactly does that work is a little more complicated because there's some renormalization involved. So again, we're going to use the laws of probability to rewrite x1 given e1 in terms of the things we actually know. In this case, we know P of x1, and we know the evidence probability, so we know P of e given x. Okay, the HMM gives you that. All right, so let's write that out. Okay, that's too much. Probability of some x1 given e1. Well, I can rewrite that as the joint probability of x1 and e1 divided by the total probability of the evidence e1. This step, just the law of probability. This is the definition of conditional probability. All right, well, how does that help us? This helps us because to compute P of capital X1, that's going to be a vector. I'm going to get a probability of each and every value X1 could take on given E1. And so I'm going to do the same computation for every single X1, which means I can ignore this constant because this constant is present for each value of X1, and I can do the computation being off by that constant and then renormalize at the end. So what that means is it's actually enough to compute the joint probability of x1 and the evidence, provided I do that for every value of x1 and then renormalize. And the probability of x1 and the evidence is just the probability of x1, which I already know, that was a given, times the probability of the evidence given x1. This has a fairly intuitive interpretation as well. This says for each position x1, each value of x1, they get weighted by the probability of the evidence given that underlying state. So if E1 is likely given x1, this doesn't change very much. If E1 is very unlikely, this P of x1 will then be reduced to a very small number. Each P of x1 gets reduced. Some get reduced more than others. And then you renormalize, and the ones that were reduced less in proportion will grow. This is why that robot, if I have some distribution that sums to 1 over robot positions, let's say it's flat over this whole room, and I get a sensor reading saying the wall is nearby, all of the positions for which wall is nearby is likely would have their joint probabilities be fairly close to just P of x1. All of the positions in the center would have their joint probabilities very close to 0, and then when I renormalize, all those probabilities that are towards the walls will then go up because we divide by some number that's less than 1. All right, so that's the key bit. Now I'll write it out here, but some of these equations are easier to go through on your own sort of mechanically. So here's how observation works. Imagine you have some current belief distribution. You have P of x given some previous evidence. So for example, we might have a belief distribution over the value x takes on at time t plus 1, given all the evidence up to t, but not including t plus 1's evidence. This is actually just the same if you're getting multiple readings of evidence at the same time. You can modify the Bayes-net for that as well. You get the same update. And so we have this b prime, which is a belief over xt plus 1, but it doesn't take into account the current evidence, and we're going to update it by feeding it evidence at the current time step. So we're going to feed it e of t plus 1. So evidence comes in, and now I want to compute what's the probability distribution over... I'll change my color. What's the probability distribution over t plus 1 given my old evidence, but also e of t plus 1? So that evidence chain is now longer. So I can write that out. I can say, well, what that is I can kind of shuffle some conditional probabilities here and say that is up to this constant here. That is the probability given, it's proportional to the probability of the old evidence, and then xt plus 1 happening, and then the new evidence happening. And so if I write that out, I can remove the constant, because it's constant over all values of xt plus 1. As long as I renormalize later. And now I'm computing the probability distribution given the old evidence, the evidence from time 1 to t, the probability that first I transition to xt plus 1, And then I observe evidence E of t plus 1. Okay? Well, what's that? That is the probability given the same evidence that first I transition to xt plus 1, and then given that I've done that, I observe the new evidence. This here is a known. This is here. So I don't have to simplify that any further. I've said my new belief distribution is actually just my old belief distribution times this quantity here that I still have to simplify, and then renormalized. All right, let's renormalize that. Let's simplify that quantity. This is the probability of the new evidence given xt plus 1 and the old evidence. Well, in a hidden Markov model, the old evidence doesn't matter. And so I get this simpler statement, which now has this very intuitive form, which says if you want to include the new evidence at t plus 1, you take your belief distribution not including that evidence, you weight every term in that distribution by the conditional probability of the evidence. Now it's not going to be a probability distribution anymore, because where it was a p of xt plus 1, now it is a p of xt plus 1 and your evidence t plus 1, given all of your other evidence. But then if you renormalize, that transfers this to the other side of the conditioning bar, and now you have a belief distribution again. So compactly, you could write this as the new belief distribution, whoops, unexpected. The new belief distribution is the old belief distribution weighted by the evidence and then renormalized. And that makes sense. Okay? Because you believe what you used to believe, except the evidence shifts things, and then your beliefs still have to sum to 1. So all that stuff that got deleted because it was incompatible with the evidence, that probability just moves over to proportionally to the other events. Okay. There's a key piece here, which is unlike so both of these basic operations, which are the building blocks of all these inference procedures, have a simple intuitive interpretation. Passage of time is you take your vector and you move it through the dynamics. Easy. Observation is tricky. It makes sense that you should weight all of the different outcomes by the evidence, but then you have to renormalize. And that's the part that's a little less intuitive, and that it will also be less intuitive in terms of how it shows up in the algorithms. It's going to show up as a step either in the forward algorithm or in the particle filtering algorithm, where you might be it might be less obvious why you're doing a certain thing, and we'll see that in a minute here. So here's an example. I could pull out the app and do this in the app. You'll see these in your projects as well. As we get observations, what happens? Your beliefs get reweighted. And the caricature is, typically, you're sort of a little confused, and then some evidence comes in, and you're a little bit less confused. So let me see if I can make this happen on the... Let's see if I can happen here. So right now, I'm sort of maximally confused. And if I get some evidence, I'm less confused. I still don't know where the ghost is, but my belief distribution is sort of concentrated on this diamond now. Now, if I get more evidence, what will typically happen is my posterior distribution will sharpen. And it did. Now my belief is sort of concentrated on these 6 squares. Let's see if it sharpens again. Okay, it sharpened. 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 That's, thank you random number generator. That's what normally happens. If you play with this app enough, you can do this in your projects. What you'll see is every now and then you get some evidence which is actually inconsistent with your current beliefs, and that actually causes you to become a little more confused. Because some things that you thought were unlikely, now they seem actually a little bit more likely. And those things that you were sure of, they don't really match all the evidence anymore. And so it's possible for evidence to come in and for you to get more confused. But the typical thing that you will see, I'm going to bust just for fun. Nice. Okay. The typical thing that you'll see is that every time you get evidence, your uncertainty decreases, and every time elapses, your uncertainty increases. Again, neither is actually something that's guaranteed to happen. The only thing that's actually guaranteed to happen is that if you elapse time a lot without getting any evidence, that your belief distribution will converge to the stationary distribution of the matrix that's represented by your transition probabilities, which means, among other things, it'll be independent of what you started out believing, assuming everything's sort of connected in a sufficiently probabilistic way. All right. Let's see a little tiny zoomed in example, and then we'll start getting into particle filtering. So there are these 2 building blocks, and in your code, you're actually going to have functions with these names in them. This is not the only way you can represent this stuff. You're going to have one action, which is to take your belief distribution and let time elapse. And we saw that is you take your old belief distribution, you multiply it by the transition probabilities, and then you sum things up in the appropriate way. There's also going to be a step where you observe evidence. And in this case, you take your old belief distribution, you weight each term by the evidence, and then you renormalize so it's a probability again. That's why this one is equal. It turns out you don't have to renormalize there, because this is a stochastic matrix here. Here, you do have to renormalize, because you took a bunch of numbers that add to 1, you multiplied them by each by a probability, so they each got either a little smaller or a lot smaller, and so you have to renormalize to get a probability again. So here's how it would work. You would start off with some belief about, say, the probability of rain versus sun. So let's say X here now is rain and sun, and E is umbrella or no umbrella. So you might have some prior on X1 that's given to you as input to the model. And then some evidence comes in. You see that E1 is umbrella. Okay, so I could shade that in here. Now we do some computation. And we see, okay, there's this 0.5 and 0.5. They both get multiplied by probability of umbrella. One of those probabilities is very high, one of them is very small, and when you renormalize, you end up with something like this. So now I think it's rainy. But then I flip to the next day. I let time pass. And I look at the probability of X2 given E1 as umbrella. All I have to do is use this elapsed time update, and things will flatten out, because if it was rainy, well, maybe it's still rainy. And if it was sunny, well, maybe it's rainy, and things tend to flatten out in this particular little model. But then I get new evidence that I see an umbrella again, and then now I'm even more sure than ever that it's raining. Okay? All right. Any questions there before we do that basically, again, sideways with particles? Okay. So one common application that people use to illustrate HMMs, we've been using sort of ghost tracking. In general, you could think about it as tracking position. Certainly not all hidden Markov models have the random variable X being position. We've had one here where it's weather. You can imagine in speech recognition it has something to do with the words that you're saying. For medical diagnosis, you might be tracking some oxygen level. In general, we are trying to construct hypotheses with probabilities associated with them over the underlying variable X, which in a localization problem is positions on a map. What we've done so far is say, here's the map, and in each square, meaning for each value of X, we're going to write a probability. That's the whole vector of probabilities. The thing we track is a mapping, a vector, from hidden states X to probabilities. That is a distribution over X. In particle filtering, you flip that around. You don't necessarily track the entire distribution. You track particles or samples, which are individual hypotheses of what's going on. You might have two samples of the same hypothesis. Some samples might not have a hypothesis, some hypotheses might not have a sample. And the data structure you manipulate isn't a map from all the different outcomes of X to probabilities, but rather a list of samples. So for example, here, you might have a bunch of samples hypothesizing you're here, you're here, you're here, you're here, you're here. And then there's other places where you have no samples representing that hypothesis, which means in that empirical distribution, probability 0. So you might need a lot of samples for this to work. And there might be a lot of hypotheses which have probability 0. So this is an approximate solution to the filtering problem. Remember, filtering is one name for the problem where I ask, given all of my evidence, what is the current hidden variable xt? Where is the robot now? That's different from the most likely explanation problem, where you want to know something about where was, basically what was the robot's road trip like that got it here. Okay. There are a couple reasons why you might want to do particle filtering. One is this event space X of robot positions might be too big to use exact inference. It might just be really big and you don't want to store it, or it might be slow to work with. Or X might be continuous. If I want to track robot positions in the real world, I can't enumerate all the pairs or triples of real numbers, right? But I can say, all right, I'm willing to have 600,000 samples. Go. And there's one sample that's here and here and here and one over by the wall. And there I get to decide how much compute I do and what the trade-off is between compute and accuracy, even if X is an infinite space like a continuous space. It's also a solution because we can now do approximate inference, which often has a lot of trade-offs, usually speed. So here's how it works. Here's how particle filtering works. Rather than writing down belief distributions explicitly, where for every outcome x I write a probability, which is a vector of size domain of x, which could be very big. Instead, I'm going to track samples of x. Maybe I track 1 million samples. Maybe I track 2. I'm going to track samples of x, not necessarily all values. These samples here are called particles. They're just samples. The amount of time I'm going to spend is linear in the number of samples because my basic flow of this algorithm is, here are my samples, they represent my current belief because, hey, all the samples are over there by the wall, I think the robot's probably over there. I'm going to do operations on these samples to give me new samples, and I'm going to do it basically by scanning over the old samples. So that's great. It's linear in the number of samples, but the number of samples you need might be very large. The thing you actually store in memory, and this is really important because some of the PowerPoint figures will suggest that all the spaces or even the ones with 0 are tracked. They're not. In memory, you have a list of samples, a list of particles. There is not a list of all possible states. That's important, or there'd be no point doing this. In practice, robot localization works this way because it happens in continuous spaces. A lot of other tracking problems also work this way, and particles are just samples. Okay, we're ready? Here is a distribution over this 3x3 grid, represented in sort of the explicit way. For each state, I have a number. In this case, some of them are 0. This is the way I'm going to draw a collection of 10 samples. 10 of those 10 samples, 5 of them are in the lower right corner. Some states have no samples. Okay? If I write out the state space, I'll have to write out 9 numbers. If I write out the samples, I have to write out some list of, okay, there's 1 in 2, 1, there's 1 in 3, 2, whatever, and I have to write them all out. I'll have to write out 10 numbers. In this case, it's cheaper to write out the state space representation. In general, it's going to be the other way around. So here's my representation. My representation of my distributions over X, which will in general condition on evidence, they'll be belief distributions, but whenever I have a distribution over X, it's going to be a list of n particles. Normally n is much, much, much smaller than the size of X. Except on these slides where it's just going to be a tiny bit bigger. But imagine the grid is huge and the number of samples compared to that is relatively small. So, we're not going to store a map that says, in this place we have 5 samples. We might as well just store the probability. We're going to store this in memory, a list of particles. When we see a green particle here in these slides, that's going to be the particle that I'm going to talk about. We're going to talk about the journey of the green particle and what happens to it. Particles aren't actually distinguished. There's just a list of them. They each have sort of the same status in the computation. So P of x will be approximated by the number of particles that have the value of x. So many, many, many values of x have P of x equals 0 in this sampling distribution. If we have more particles, we'll get more accuracy. Right now, imagine all the particles have equal weight. So if I show you this list of particles here, I could ask you a question like, hey, what's the probability that the robot is at this location, which is 2, what is that? 3, 2. So I would look through and I'd say, well, there's a 3, 2, and there's a 3, 2. So 2 out of 10, that is my approximation. Is that right? It's probably not right. This is like any other sampling method. Unless you have a lot of samples, you're going to have some error due to the sampling noise. All right. So I'm going to be carrying a list of samples, a list of particles, which represent my current hypotheses, and in aggregate represent my belief distribution over where the robot is. It could be here, it could be here. And at 3, 3, I have 5 samples. That represents I have a higher probability there. How should I take this list of particles, which represents my probability distribution, and advance time? Well, what happens when time advances? The dynamics come into play, and for every xt, there will be some distribution over xt plus 1, which represents what happens next in the dynamics. And so what I'll do is I'll go to each particle and I'll just move it. Like, think about moving it around the game board here. And for each sample x that I have right now, I'm going to take a sample of its future. Well, if it's at value little x, I'm going to look up the transition probability and say, oh, here are the probability of the various x primes, and then I'm going to sample. I'm going to use my multinomial sampling that we had before. I'm going to take a uniform distribution from 0 to 1. I'll map it onto the various outcomes, and let's say it'll go to the square below. That is my new value x prime. So for example, this green, let's go green. This green particle here is at 3, 3. I will look up and I will say, in my HMM, where do things go from 3, 3? And it'll say, well, 60% of the time they go to the square below, and 20% of the time they go to the square below and to the left, or whatever it is. And then I'll flip a coin, and maybe it goes to the square. That particle will be replaced by a new particle at this newly sampled position. So each particle before turns into a particle after. And each one takes its own journey. So if I have 5 different particles that all happen to be at 3, 3, for each one I'm going to pick it up and say, hey you, where do you want to go? I want to go down. Okay, great. Where do you want to go? I want to go down. Great. Where do you want to go? I want to go to the left. And so they will sort of, in general, sort of scatter a little bit. But each one is independently picked up. You go through this list, pick up each particle, and sample a future for it. Even if 2 particles are the same, they will in general not have the same future. And you can have 2 particles that are different that end up having the same future because there are multiple ways to get to a certain square. This should remind you of prior sampling. Things that are more likely in my distribution are that increased likelihood is reflected in the increased count of samples. So the sample frequencies here are going to reflect the probabilities. And then each variable I'm just going to sample a future for, just like prior sampling. Oh, you chose sprinkler on. Let's sample for wet grass. And so for each of these samples, I'm going to be, oh, you're in 3, 3. Let's sample a future for you. So each particle before becomes a particle after, in general, sort of evolved according to the dynamics. And this is going to capture the passage of time. If you have enough samples, these will look, pretty much like the exact values before and after. If you only have a couple samples, it'll be super noisy. Okay. Any questions? All right, so this is actually a lot easier. I think this is a lot easier to get intuitively than the actual exact inference, because I don't have to think about sort of marginalizing probabilities or anything. I just have to think, all right, here's a hypothesis. Maybe it's in 3, 3. If it were, where would it go? I'll flip a coin. The fact that there are now a bunch of particles here, well, how did they get here? Well, they all started at a different location. They all flipped a coin about their future, and then they transitioned here. That is just the summation weighted by the transitions of all the previous probabilities, but it's done in a sort of more sample-based way. Okay, here's the trickier step. Then we'll look at some examples and take a break. The trickier step is observation. So I've got a list of particles. So here they are. This is what is actually in memory. This is what I put in PowerPoint so we can visualize it. Okay? So you've got this list of particles. And I could look at this list of particles and I could ask questions like, how likely is it that you're at 2, 2? Well, I've got 1 particle there out of 10. Looks like 10%. I could ask questions like, what's the most likely location of the robot? And according to these particles, it's 3, 2. Okay. I can also use these particles to incorporate evidence. So let's say I get evidence that this square here measured a reading of red, meaning ghost very close. Well, if this were prior sampling, or more to the point here, rejection sampling, what I would do is I would pick up 3, 2 and say, all right, time to sample a future for you. What reading do you think should happen? And I'll be like, oh, I think orange, dead. And then you pick up the next one. What do you think should happen? Yellow, dead. And you reject all of these samples by asking them what evidence they would like. And then when it doesn't happen to match the evidence you have, which is red, they're out. This is a way to reject all your samples. Okay, so we don't do this. Instead, we do something that's like likelihood weighting. I pick up each particle and say, hi, particle, I'm here to inform you that there is this evidence red at this square. And the particle might say, great, that's probably what would have happened anyway. And so this particle maybe says that. There are going to be other particles that say, I think that's extremely unlikely. And so each particle will stay there in your list, but it will pick up a weight because we're now doing likelihood weighting. We're not giving them the option of being rejected. We're forcing them to stay around, and so they can only stay around fractionally. They can stay around with a fraction that represents how likely it would have been to generate the evidence in question. So now suddenly we have the same particles but weighted. You can think about that as some particles stay size 1, but most particles shrink. Some particles shrink a lot. Maybe some particles will shrink down to 0. So suddenly instead of 10 particles, I've got like 3 fractional particles. But I do still have 10 things in my list. What does this correspond to? This corresponds to taking my belief distribution, my old belief distribution, and weighting everything by the evidence. Except, remember, when I weight everything by the evidence, I have to renormalize. Why do I renormalize? I renormalize because I don't have a probability distribution. Here, I have samples, but a lot of them are sitting there with tiny, tiny weight, maybe even 0 weight. So I need new samples. And so there is another step that we add after we've downweighted all of the samples by the evidence probability, where we get new samples weighted from the old samples. Okay? So what we're going to do is we're going to take these weighted samples, which are the old samples we had, and some have shrunk a lot and some have not shrunk, and I'm going to say, these samples are no good to me because their weights are starting to shrink, and if I do this for too long, their weights will all go to 0. And so what I'll do is I'll create new particles. The new particles I sample with replacement here from the old weighted samples. So I say, all right, what particle should I have for the first thing on my list? Well, I come back up here and I pick one of my old particles in proportion to its weight. So this one here at 3,2, which has weight 0.9, it's going to get picked more often than this one at 1,3, whose weight's approaching 0. And so you might find that that particle at 3,2, which was one highly weighted particle, it might show up now as multiple unweighted particles. And so we've sort of, by resampling, shifted the information about their relative probabilities from their weights over to their multiplicity. So how's that work? We had n particles. We're going to choose n different particles from our old particles with replacement, and in the process, we'll ditch the weights. The weights were necessary to reflect the fact that, say, this one here was present, but like basically shouldn't contribute very much to the belief. That same situation is reflected in the fact that with high probability it won't be selected. And now your update's complete. So when you observe evidence, you take your particles, you weight them by the evidence, and then you resample them. And now you have another set of 10 particles which are composed of your old particles, some of them more than once, and some of them have dropped off. Then time will pass, and those particles that are sort of cloned from each other will start to diverge, and so on. All right, so let's do a recap. We'll see some demos, and we'll take a break. All right, particles track samples of states, or hypotheses of unobserved variables, rather than a distribution. So instead of tracking a distribution, I track this list of particles. When time elapses, I move my particles around the game board probabilistically by picking each one up and picking a future. I don't have to renormalize. I don't have to resample. It's just each particle moves. Multiple particles that had been in the same place can diverge. Multiple particles that had been diverged can come back together. It's whatever you sample. When you get evidence, you weight the particles. Some of the particles maintain high weight because they're compatible with the evidence. Some of the particles are starting to shrink. They're almost gone. You don't want to keep around particles that are basically not contributing because they don't represent very much mass of your belief distribution. And so you take those weighted particles and resample, which gives you a new set of particles, once again unweighted. There's some multiplicity, and they represent your new distribution. Elapse time, this represents what happens to your distribution if time passes. Weighting and resampling together represent what happened to your distribution when you observe evidence. Okay, let's see some examples. We'll take a break. All right. So, Ghostbusters. We will run the same Ghostbusters app where we can elapse time or take observations or bust the ghosts, except this time, instead of exact inference, we will be doing it with particles. Each particle will represent a hypothesis of where the ghost is. So, in memory somewhere is some list of, 30 positions where the ghost might be. What's being visualized? What's being visualized is, according to those samples, what is the probability implied over this space. Luckily, the space is small enough I can do that computation. In general, I would just have my particles. You'll notice that some of the positions have probability 0 because there's no particles that live there, and others have probability, greater than 0.02. And that's because instead of sampling everything uniformly, the samples fell where they fell, and there's noise in that process. So here's what, with a moderate number of samples, a uniform distribution looks like. It's not all that uniform, right? What happens when I elapse time? Well, all these particles will swim around in a circle in a stochastic way here. So there they go. If I do it fast enough, you can actually see the circular motion there. Okay, I can gather some evidence, like, oh, this one looks reasonably likely. Let's sense here. All right. So you can see what happened when I gathered evidence. A whole bunch of particles wiped out because they didn't match that evidence. And then a bunch of new particles were sampled from those weighted particles. A disproportionate number of them happened to be right here. Maybe I'll sample here. All right. So a bunch of particles that were all piled up there that are now inconsistent with that evidence just basically got deleted. They got small weights and then they didn't get resampled. So where did my mass go? It went to sort of wherever there were particles that were still reasonably likely that have survived the previous round. So at this point, the particles are starting to clump together, but they're not probably in the right place. Okay, this is why it's dangerous to have a small number of particles. And it's always dangerous to have a small number of samples because you're going to get noise from that. But in particle filtering, there's this extra tendency of particles to sort of like accumulate in weird places and get overly peaked in their distribution. All right, let's do that exact same thing, but with one particle. So what do? I'm going to have my initial list of particles, which will represent a uniform distribution over the space. There it is. That's as uniform as you get with one particle. All right, I can elapse time. What's going to happen? Well, a particle's going to sort of swim around in a circle. I can take a measurement. What will happen? Let's measure over here. All right, where's my particle go? It stays right there. There's kind of nowhere for it to go. It gets downweighted, and then you sample a new one, and guess what? You've only got one choice, and your particle's back. And you can't shake this one particle. It's never going to split and become two particles. Each particle just sort of does its thing. Only when you have multiple particles can you have one get resampled a few times and another one sort of get lost in the resampling shape, in the resampling step, and this causes your distribution to sort of refocus. All right, let's do it again, but with a ton of particles. Okay, now there's a lot of particles here. And now you can see this, there's some noise, right? In fact, there's a 0.01 here where it really should be 0.02. But this is a lot closer to the actual distribution because the number of samples is higher. So let's grab some evidence. All right, now if I let time pass, all of those particles will start to diverge. And now they're sort of smeared all over the place. Now if I take some samples, almost all the particles are living here, but if time passes, those particles start spreading out. And all those things that happen to particles, the same thing happens to the probabilistic distribution. Okay. We'll bust. Okay. It's approximate. Okay, so let's now take a break, and then we'll see some demos of what these techniques can do. 2-minute break. Okay, let's start again and see some demos of what this looks like in practice. So most of the demos we're going to see now are robot localization demos in one way or another. Sometimes the robot will be a ghost in Pac-Man. In robot localization, you imagine you know the map, but you don't know the robot's position. So think, what is a hypothesis in this case? That will usually tell you what the underlying variable x is that you're trying to track. If the hypothesis is, I think the robot is here in a known map, that's robot localization. So x here, the underlying variable that you'd like to reason about, is the robot's location on the map. E, the evidence, observations, might be something like rangefinder readings. So in a lot of these cases, as shown here, you have some robot, you're not really sure where it is, and the evidence you get is you have a 360 rangefinder that says far from an obstacle, close, 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 close. That tells you there's sort of a wall behind you and to the right. In these cases, with real robot localizations, the state space and the readings are typically continuous. There's some rangefinder reading, which is a real number, and your state space is some sort of map with maybe polygonal objects or something, depending on how that's specified for you, and you're somewhere in there. The robot can be at any real location. So it's really appealing to use particle filtering, but of course, your particles can't be everywhere in a real space. So it might look something like what's shown here. There's a map. The gray areas are obstacles, walls, furniture, and so on, and all the little red dots are places the robot might be. This is a case where the particles are sort of smeared all over the map, and if you stare really hard and the resolution's high enough, you can see there's a lot of places that don't have any particles. And what if the robot's there? Well, in general, in particle filtering applications, you're going to have a cloud of these things, and you're going to ask questions like, well, what's the average location? So even if there's no particle in the exact correct hypothesis, it's still very useful because you're working with the whole cloud of them. So particle filtering is a main technique. Let me show you a couple examples. This is an example from University of Washington where you're going to see a robot. So there's actually a robot in this map that's shown. You don't know where it is. So there's particles everywhere to begin with and a whole bunch of them. And the robot is going to get readings that say there's an obstacle in front of you but nothing to your right or left. And so it's going to get these distances which are shown here as blue lines. And of course, not only don't you know where the robot is, you also don't know which direction it's pointed. So your hypothesis is not just a dot, it's sort of a dot with an arrow. And as the robot moves around, new readings come streaming in. So if I say, oh, hey, I'm pretty sure there's a wall behind me. Well, I could be here, I could be there, I could be there, I could be there. And then as I move around, I start to see, hey, wait a minute, there's not a stage here that I expected. And so I know I wasn't at that wall. And so I'm going to run this, and you can watch the particles. And each particle, think of like a hypothesis. Robot might be here. And as you move around and you start to get evidence that's not consistent with all of those hypotheses, a lot of the samples are going to die out. They're going to die out by getting downweighted, and then during resampling, in general, they're going to not get reselected. Okay, so let's go. Right now, it has no idea where the robot is. There's some most likely hypothesis, but it has no idea. The robot's actually going down the corridor. And it's getting all these readings that say wall to my side, wall to my side, wall to my side. So you'll notice that already it's gotten a whole bunch of readings of wall to my side as it's been moving forward. So what does it know? It knows that there's a wall next to it and that it was able to move forward along a wall for a while. And all these red dots that have survived are ones that are in locations where you would have moved past a wall for a while. So all the little rooms that aren't big enough to support that reading of a wall as you move forward, they don't have very many particles in them. And you'll see this distribution is going to start to collapse as you get more and more evidence as to where you are. So once you've seen a wall for a very, very long time, off to your side, you know you're not in the square off to the left. And so now it's getting to the point where it knows it's along a long corridor, but it's not really sure whether it's on the left end or the right end. And then watch what happens here. Okay, now he knows where he is. Let me back him up. Okay, right here. Can I stop it? Okay, right here, if you had to guess, you would say, well, the densest cluster maybe of points is over there on the right, and you can see that's where the visualization has guessed the robot position is. The robot's continuing to go forward. One of two things will happen very soon. Either it will get a rangefinder reading that says there's a wall in front of me, at which point a whole bunch of dots to the left are going to disappear because they're not consistent with that evidence. or it's going to see more corridor. And then a whole bunch of dots to the right are going to disappear because they're not consistent with that evidence. And as soon as that happens, it's going to be pretty much localized. And it turns out no wall appeared, now it knows where it is, and it can sort of wander around. And there's this cloud around it. You'll notice anytime it turns, there's sort of a bloom of uncertainty around its position, but now we're basically tracking it. So that first phase was really localization. Where am I in this map? And then once we were localized, sort of monitoring our location, once it had collapsed down from enough evidence, is sort of an ongoing thing that's more like robot tracking. Okay, first you're figuring out where you are, then you're tracking where you are as you go, but mathematically it's all the same thing. All right, here's a laser rangefinder of this. It goes by pretty quickly, but imagine each of these hypotheses is consistent with the evidence, and the robot knows by now, based on its movement pattern, that it's somewhere in the hallway, and it knows it's about to turn into one of these two symmetric rooms. This is how I feel whenever I get off the soda elevator. And then it's either going to see a piece of furniture or not. And if it sees a piece of furniture, it's going to be in the upper room, and if not, it'll be in the lower room, and wipe out on the lower particles because it saw the furniture. Okay, so this is sort of the way this goes. You have a bunch of particles. They represent, in this case, sort of two primary groups of hypotheses, and then evidence comes in that sort of deletes a whole bunch of those particles. Okay, any questions on that before I talk about? Yep.
If I know exactly where the robot starts moving, do I need to use the particle filtering to find this?
It's a great question. What if you know where the robot starts? You still want to do this because you won't know where it is for long. Because imagine it's basically like how we localize. I know exactly where I am. If I close my eyes and I just start walking, I will have a reasonable sense for a while, and then I'll probably hurt myself. And what happens is the robot, you give it a command like go forward a foot, and it goes forward 11.3 inches. And then you have it turn, and it turns almost what expected. And these little errors start to accumulate. This is equivalent to elapsing time. Over time, your uncertainty is going to bloom, and that distribution is going to flatten because your transition probability says wherever you are, if you move forward, you're going to be a unit forward with some noise. And that with some noise is going to add and add and add. What you want to do is you still want to use something like particle filtering to track how that uncertainty grows and is then mitigated and reduced by the readings you get. And so you could think, well, if I really know where I am, maybe I should use another technique. But in fact, the sort of value of particle filtering is especially high when you know where you are. And you'll notice in this here, the number of particles they use is adaptive. And so you start with a bunch of particles, or relatively speaking, a bunch of particles here. You start with a bunch of particles because you have to cover all these hypotheses. You might as well actually have enumerated a grid of probabilities. But once you basically know where you are, you can just keep a cloud of hypotheses around you, which is basically like, I'm still there, I've drifted left, I've drifted right, except instead of enumerating the hypotheses, you just sort of blanket your nearby area with random samples. And that's really good because it means you don't have to think about sort of the local geometry or anything, you just blast samples everywhere. Okay. Here, you'll notice the particles now, if I can make this go away, the particles now are starting to drop because the more peaked your distribution, the fewer particles you need. But you got to be really careful because at some point the math is going to tell you you are completely sure you're at this particle. And remember that lone particle? It's bad when you have a lone particle. So you need to generally sort of maintain a cloud of hypotheses to catch that uncertainty as it blooms. Any other questions? That was a great question. Yep. How do you determine the number of particles? That's a really hard question. There's no kind of hard and fast rule. Often in these environments where you're kind of repeating these things, you kind of can figure out what the right number of things is to track. It's going to depend on the complexity and the level of uncertainty, and there's no hard and fast rule. There's some signs you don't have enough, like distributions collapsing. And there's signs that you have too many, like particles are all lining up on top of each other. But there's no... There are some things that can be said about required number of samples, but in practice it's hard. It's hard to know. Yep. Great question. How does the robot move? In all of these things I've shown you, the robot's intended motion, meaning the dynamics, is known. Somebody is saying move forward or turn now or whatever. So there's no action selection. It is simply tracking what's going on. in actual robot planning, you would have to make the decision based on some other goals. Maybe you're trying to move a package from here to there. For this tracking, you know where the robot is trying to go in the form of the expected behavior under that transition probability. If the robot's trying to stand still, you're not going to get any new evidence and you're never going to figure out where you are. On the other hand, you won't actually accumulate any true uncertainty. Okay, let me show you something else, which is pretty cool. It's called SLAM. It stands for Simultaneous Localization and Mapping. This is where your hypothesis is not, I'm here on a known map, but I'm here and I think the map looks like this. So you don't know the map. That means each particle is a map that you are drawing with a dot on it. Okay? Instead of like a grid of these things, there's some high-dimensional space of maps and dots on them. So let's take a look. In this case, how do I visualize it? Well, I can't have each dot be a map anymore, but I can take all the hypotheses, each of which is a map with a red dot in it, and I can sort of superimpose them according to a visualization. And so what you'll see is, in addition to like the ballooning out of where I am on the red dots, the map is also going to sort of be blurry when I'm not really sure exactly where that wall was or which direction it went. And so as you go, you're sort of mapping, but you're not totally sure how long this corridor is. And that flash was you had a whole bunch of particles that diverged. So you can see here your space, your estimated position is in red, but you're not really sure where you are, and that's leading to not really being sure how far this wall in front of you is because you don't know where it is with respect to the rest of the map. And as you start going around this loop, what's going to happen? Right now you've sort of gone around in a circle. And as soon as you see your starting point, a whole bunch of hypotheses that perhaps this is a big spiral are going to vanish and everything's going to snap tight right about now. So this is a case of sort of maintaining a whole bunch of different kinds of uncertainty over multiple variables and sort of using them to disambiguate. Let me show you another vehicle of this. Another video. Okay. So you can see here, again, this is showing its trajectory. It's on one of these trajectories, but as it goes around, it gets less and less sure exactly where it is until it sees its starting position, and suddenly everything sort of goes rectilinear here, and a lot of those hypotheses which correspond to having drifted when in fact you didn't or whatever it is go away. And you can see there's a bunch of snapping to rectilinear shape that happens when you see reference points. Okay, localization and mapping. I think it's super cool. Any questions on the localization and mapping? And then I'm going to leave you with one thought on how this is going to apply to your projects, where you will have more than one variable. Okay, let's quickly take a look at projects here. The general case of a hidden Markov model. So what is a hidden Markov model? It's a super simple Bayes net where you have X and evidence. But it's interesting because it's replicated across time. You can also take more interesting Bayes nets, which have a bunch of variables with dependencies, and replicate them across time. This is popular for things like, medical diagnosis, where there's a bunch of different underlying things. They have connections between them. They all evolve over time: oxygen levels, heart levels, whatever. For DBNs, dynamic Bayes nets, you want to track multiple variables over time, which have correlations amongst them, using multiple sources of evidence. The idea here is you're going to take, instead of this tiny little Bayes net and replicate it, you're going to take whatever fixed Bayes net you have and replicate that at each time step. And you're going to specify not only how things interact within time, but across time. So here's an example of that. Let's say you had 2 ghosts instead of 1, and you had a sonar reading that said, I'm very far from the red ghost sound, but it seems like I'm really close to the blue ghost sound. Well, you could have Ghost A and Ghost B, which are 2 different random variables, each of which has an observation. And this could replicate across time. So here's time 1, which has the variables, and then at time 2, those variables repeat, and you can unroll this network as far as you want. This is what you're going to have in your projects, where the thing you're going to reason over is where are multiple ghosts on the evidence of multiple sonar readings. So I'm going to show you what this looks like in 2 demos, and then we'll wrap up for today. All right. So here is Pac-Man. I'm going to control it. And what you're going to see is sonar readings. These are down in the lower right. Actually, this is super hard to play. Those numbers in the lower right show you for each ghost color how far you are. It's a noisy signal. So I'm going to try to hunt down the blue ghost. Okay, that's the wrong way. That's the wrong way. That's really the wrong way. This is super hard. Okay, he's here somewhere. Got him. Okay. Now I'm going to go try to track down another ghost. Anyway, it's very hard to know where the ghosts are given these readings. The best I can do is, it looks like I'm getting close, it looks like I'm getting far. I can play hot-cold with these ghosts. But you can take these readings and a model of the ghost behavior and synthesize them into a localization of the ghost. And that's going to look something like this. All right. And so you can see here, these are clouds that represent your beliefs over the ghost location. And you might think, well, that's great. You're running 4 HMMs. Okay, it's still super annoying. You're running 4 HMMs. In fact, the ghost dynamics in the project will be such that they sometimes do things like go towards each other or disperse and go away from each other. So the hypotheses you are tracking are multiple ghost locations simultaneously. Each hypothesis is this ghost is here, this ghost is here, this ghost is here. So the event space is very big, but a particle is very simple. Here's what I think is going on. Also, here's what I think is going on. Also, here's what I think is going on. And you have 1,000 of those hypotheses. And even though it's a high-dimensional space, they cover a lot of different ghost positions and let you compute these sort of marginals that you can use to chase the ghost down. All right, that's your project. We'll see you next time for starting our unit on machine learning.